Today, I'm going to speak about probability and go to certain, some basic definitions and what is expectation, and we will see how far I get. So let me say something about, I'm not going to assume that you have any background, so I'm going to cover the basics, but I'm not going to do it very formally. So the notes have the formal definitions and also have proofs of claims. For a lot of easy claims, I'm just going to state them, and if you're interested in the proof, look on the class notes. And that's it, but I would try to avoid doing various silly proofs that, anyway, if you had some probability at some point, you might have seen them already. And some of them are also very intuitive. Now, probability, unfortunately, probability is one of those things which is very intuitive, but also extremely counterintuitive, which is very bizarre. So it's very easy to get very confused and get things wrong. So with probability, it's really important, especially with discrete probability, it's really important to kind of think about it carefully and elaborately. And also probability in general is a pretty deep field mathematically, because what happens is that when you speak about continuous variables and you start speaking about probabilities, then you very quickly deteriorate into integrals, and then it becomes very important to know what probabilities can be computed, I mean, which integrals can be computed or not. So probability deteriorates very quickly into measure theory, and things becomes very deep, right? So we are not going to go into all those things, but it's kind of useful to know it, because there are a lot of, if you look on the formal definition of a lot of the stuff I would use in this class, the definition looks overly formal and complicated. And the reason why they are complicated and so on is because, in fact, if you go all the way into probability, things are delicate and requires quite a bit of thinking. Okay, so with no further ado, let's start speaking about what probability is and so on. So the basic way to think about all of this stuff is that we are doing some experiments. In our case, usually the experiment would involve running an algorithm, running an iteration of the algorithm, whatever it is. And after we do that, we want to understand what the process did, right? So the way to think about it, you do an experiment, think about it in a physics experiment, you do some experiment, and then you take some measurement. The value of the measurement is going to be called a random variable. So maybe let's define it more formally. So omega is called a sample space. And the way to think about sample space is this is all the possible result of the experiment, right? And it might not even be possible to decide which exact element in this sample space happened in your experiment, right? So sample space, the element of the sample space are called atomic events. Or if you want, elementary event. Okay. But usually when we speak about an event is usually going to be a subspace of omega. It's going to be just a collection of atomic events, right? So think about, let me start with maybe with a silly example. You take a dice that has labeled 1 to 6, the faces, you roll it, you get a number between 1 and 6. An event, for example, might be you got an even number, right? So the event here would be made out of 3 atomic events, right? Dice is even, sorry, event dice is even. And this is really going to be the set 2, 4, 6, right? So it's a set made out of atomic events. Okay. And of course, we will be interested in the probability. So what is a probability? So I'm going to somewhat oversimplify for a second. Probability is a function that assigns every subset of the sample space a value between 0 and 1. Okay. Now we're going to require 2 properties of this probability function. The first is that the probability of the complete set is 1. This is property 1. The second property is that for any xy in omega such that x and y are disjoint, we have that the probabilities add up. Probability of x union y is equal to probability of x plus probability of y. So this is the 2 properties that require with probability function, and it is to prove that this has a lot of desired properties. In particular, the probability of the empty set is 0, and we will see more stuff useful later on. Usually, in our in the most basic setting of rolling the dice, every atomic, the sample space is the 6 number 1 to 6. Each one of them has equal probability, and then the probability of an event is just the size of the set divided by 6, right? So everything is very simple. Okay. Now I should mention that usually, if you look at the formal definition, you don't speak about the power set as I did. There is this mapping from F to 0, 1, where F is this subset of the power set, and you require various properties from it. So this is the various properties required from the set. It's called the sigma algebra. And I'm not going to go through what exactly it is. It doesn't really matter. For our purposes, at least in this stage, you could just think about it as being the power set. Okay. Okay. So the first useful thing to know about probability is the union bound, which one can prove it directly from what we had seen, which is that if I have a collection of events, E1, E2 to EM, I have a collection of events from my sample space, then the probability of the union of the EI is smaller or equal than the sum of the probabilities. Sum of I of the probabilities. Okay. Yeah, I know this is a bit dry. I'm going to get to more interesting stuff shortly. I hope so, at least. Right. So usually, okay. So now I need to define what is a random variable, which I kind of mentioned, but let me do it formally. So random variable is essentially a measurement, right? A measurement means that you do an experiment and then you measure something, right? Like, for example, is the dice number even or odd, right? It's just, it can be a true-false variable, it can be a 0, 1, it could be some real function of the experiment, you measure temperature, what is the temperature? But it could be a lot of other things. We will see other examples of random variable. It might be some function from the sample space into sets or whatever, right? It's essentially the way to think about it. It's a mapping, random variable is a mapping from the sample space to some target space. right? But the way to really think about it, you're doing an experiment, you're doing a measurement, the result of the measurement is the random variable. Sometimes people write random variable as RV, right? It's a shortcut. Yeah. Okay. So this is random variables. Now, the thing about random variables in general is that think about you have some random variable. Usually we will use capital letters to write random variables. And the problem with random variables is that usually to understand them, we want to know, we need to have full information, but full information is too much to ask for. It's too much, right? It's like for every possible value, right? So if X can take, for example, values from the integers, right? What we really want to know is that, you know, for any I in the integers, we would like to know what's the probability that X is equal to I, right? And you think about it, there's an infinite table and specifying this function, the probability function. So this is too much information. So we want to understand the probability, how the probability function look like, which, by the way, when we speak about probability, sometimes we call it distribution. But we want a much more compact way to describe it, right? So we're going to have this kind of summaries, which would be useful to understand what probability is. And of course, the first one is expectation. So expectation of a random variable. Okay. So the expectation of X, this is going to be the sum. This is over all values. So this is X times the probability that X is equal to X. Okay. Again, I'm assuming you already know what expectation is, but again, just due diligence and remind you what's going on. So the expectation is just the average value of the variable. So think about the random variable as being a real number, right? And we do the experiment, we measure the random variable, we get the value, we write it down, and we repeat the experiment a large number of times, right? If we do it a large number of times, the value, there's going to be, you could take an average of all the values you encountered so far, and this value is going to be an average. And if you think about it, this average would converge. This is kind of the average value of the variable, and the expectation is exactly this value, right? And formally it just says, you know, for every value X, you ask what's the probability of having this value, and you just add it up. You're essentially doing a weighted average of the values of the random variable, and you get the expectation. Sometimes we will write it as mu X. So this is expectation. And expectation is already useful because it tells you what's the average of the average value of this random variable. It gives you one numbers that give you some information on the distribution. It's not too informative, but it's already enough to do some interesting stuff. Now let's talk next about another interesting concept, which is called conditional probability. By the way, are there questions so far? I know this is just some basic probability stuff, but still, if there are questions, I'll be happy to answer. If there's anything in the chat, didn't hear anything, but so conditional probability is very interesting, and again, it's one of those things that it's a bit confusing when you see it for the first time. So the idea is that you have two random variables, X and Y, two random variables. And they might be completely unrelated, they might be related. We don't know, you know, at this point, we are not assuming anything. And now we're interested in the question of what can you tell me about the value of X, right? If I tell you the value of Y. So let me write it in words because that's kind of important. Probability of X to be small x, given that Y is Y. Right? So the way to think about it is that you're doing an experiment. A priori, you don't know anything. You did some measurement. This measurement gives you the value of Y. And I reveal to you the value of Y. And then I ask you, what can you tell me about the value of X, right? So for example, think about, let's maybe do an example. X might be, yes, X would be, let's say, 1, if and only if the dice is even. So again, I'm rolling a dice. That's my experiment. And X is 1 if it's even, 0 otherwise. Okay. And I'm going to define Y to be 1 if and only if, let's say, the dice is smaller or equal than 3 and 0 otherwise. Okay, so by the way, those random variables that get values of 0 and 1, or more precisely, random variables get 1 if an event happens and 0 otherwise, those variables are called indicator variables. They're super important. We will use them all over the place. And they call indicator variables because they indicate whether a certain event associated with the variable happened or not. And it turned out somehow to be very useful. Okay, so in our case, for example, if I tell you that, let's see, probability of X equal 1, given that Y is equal to 1, right? So this is the probability that X given 1, given that I told you that Y is equal to 1. So let's try to think about it. Does it mean X equal to 1? It means that the dice is even, right? So the dice have to be either 2 or 4 or 6, right? Given that the dice was Y equal 1 means that the dice was smaller than 1. So D is equal to 1, 2, or 3, right? Okay, so, and since the number have equal probability, this is equal to third, right? Which is not especially interesting in this case, but still. It's still kind of interesting if you think about it, right? Because probability of X equal 1, right? The dice is even, this probability is half, right? But now that I told you that Y is smaller or equal than 3, so the dice is smaller or equal than 3, then the probability decreased to a third. Okay, so that was an example. Now, the right way to think about these conditional probabilities, maybe I should use a different color. So you have the probability space. Okay, and we have 2 events, right? Let's call this, this is X equal X, and this is Y equal Y. Let me use a different color because that will make things clearer. This is the event Y equal Y, right? Now, when I tell you that y equal y happened, I essentially said that my sample space is restricted to this area, the purple area where y is equal to y. And now I'm asking for what is the probability that x is equal to x. Namely, I need to be in this region, which is the intersection. Right? So this is probability of x equal x. Oops, write it again. X equal x and y equal y. Right? So the way to think about it conceptually is that the probability is the area, right? So this is the area of this black lens, and I have to divide it by the area of the purple area, right? So this is the area of py equal y. So this is formally the definition of conditional probability. Probability of x equal x, given that y is equal to y, is probability of the intersection divided probability of y equal y. Okay. Now, so this is conditional probability. And the reason why we need to speak about conditional probability, because I really want to speak about independence. Independence is like, independence probability is like freedom for Americans. It's something that you want, but you can almost never get. And you speak about it all the time. So two random variables and I guess most of the people don't know what it really means. If you want to continue the carry on this story, this analogy. Okay, so two random variable x and y are independent if. So let me first tell you the informal definition, which is more useful than the formal definition. The informal definition says x and y are independent if you know the value of y, it tells you nothing about the value of x, and vice versa, right? So formally, that means that probability of x equal x, given that y is equal to y, this tells you nothing, right? Which means that this just have to be equal to the regular probability. You gain no information from knowing the value of y. And if you go to the calculation, this really implies that probability of x equal x and y equal y is equal to probability of x equal x and probability of y equal y. Okay. So this is the definition. Those two things are equivalent. Right, this is by definition. So that's what it means to be independent. And usually it's very easy to decide what things are independent. As I hinted, independence is rare. It's a very strong condition and it's rare. Fortunately for algorithms, sometimes we can enforce it, right? We can make the algorithm can make decisions that are independent by repeatedly rolling the dice independently and so on. But when you try to understand real world phenomena, there are usually the correlation between things and dependence between things. And in a lot of cases, we don't really understand the correlation. Okay. Questions about this so far? Okay. So now we can get into some useful properties and hopefully get back into algorithms shortly. So let's speak about some property of expectation. So an important property of expectation, this is one of those magical things for any x, y random variables. we have that the expectation of x plus y is equal to the expectation of x plus the expectation of y. So this is this amazing property. So this property, by the way, you can prove it directly from the definition of expectation. I'm not going to do it. The important thing here is that I'm not assuming in any way that x and y are independent. They don't have to be independent. So, so this is called linearity of expectation. It's a super, again, super important property. Somehow probability have a lot of those things where things that are kind of obvious, linearity of expectations, turn out to be very powerful and very useful. That's why I'm talking about in such details. In general, expectation is a linear operator. So what do I mean by that? I mean by that expectation of one thing we already saw, right? Expectation of x plus y is just the sum of the expectations. So that's good. The other thing is that the expectation constant times, if you multiply x by c, c is a constant, then you can take it out. This is just c times the expectation of x, right? So expectation behaves like a linear operator, which is a useful thing to have. And we already can get one very interesting, fun algorithm. But let me do 5 more minutes of some probability background, and then we will move to the algorithm. So another useful lemma to remember, the expectation for n. Okay. So now we have to run variables that are independent. It's really important because otherwise this is not true. Again, the random variables are real values. The expectation of the product is equal to the product of the expectation. Again, this just follows from definition. You have to do the calculation. It's 3 lines of ugly calculations. There is nothing there. The proof is, of course, in the class notes. Okay. So let me now speak about variance a bit. So as I said, one thing that we have is the expectation, the average value. But the problem is that we don't know the expectation doesn't tell us much, right? Because think about a case where we have a random variable that gives us -1 and 1 with probability half. The expectation, of course, is 0, right? But think, on the other hand, on a variable which is, maybe I should do it on the left. Think about a similar random variable where this is -10 and +10, again, with probability half. The expectation is 0 too, right? So somehow I want to be able to say the expectation would tell me that those two things are the same, but one of them is much more stretched than the other. So variance is a way to get one number back that tells me how stretched the distribution is. So formally, the variance of a random variable x is the expectation of x minus mu squared. Okay. What is mu? Mu is just the expectation of the variable. in this case. Right. Okay, let's use some of the stuff we saw before, right? So let's open the squaring. So this is x squared minus 2x mu plus mu squared, right? Mu is just a number, right? And I can use the linearity of the expectation. So this is just the expectation of x squared minus 2, the expectation of x. To remind you, mu is a number, so just mu plus mu squared. So this is just the expectation of x squared. This is mu, right? So minus 2 mu squared plus mu squared. So this is just the expectation of x squared minus mu squared. Right? So this is a very bizarre quantity, and intuitively what it measures, let's look at the original definition. If you look at the original definition, we look at the distance between x and its expectation, right? So how far is it from its average value? And then we square it. We square it because mathematically squaring is much, works better than absolute value. But at some level, you can kind of think about taking it as absolute value. So we kind of measure how far the variable on average is from its average, which is two average in the same sentence, which is not good, but it is what it is. Okay, and clearly for those two distributions I drew here, I will get two different, completely different values. Okay. So variance is sometimes called the second moment. Second moment. And we will see why it's called the second moment later on when we define other moments. Okay. Okay, now I'm going to mention some things very quickly. I guess another 5 minutes of probability, but then I'm really done with probability for the sake of probability, just because I need you to make sure you know about this. So Bernoulli trial or Bernoulli distribution is essentially a coin flip. You flip a coin and it succeeds with probability P. And so this is, let me write it, Bernoulli. Bernoulli distribution. Okay. So flip coin with probability P for heads. And then you get 1. Otherwise, 0, right? So this is a random variable, right? I flip a coin. If it heads, I get 1. If it tails, I get 0. And the probability for heads is P, right? So usually you write down, you can write things like X distributed. We're not going to do it, but just for if you see it, right? So you might see something like that. X, this is tiled, it says like, X distributed like Bernoulli with probability P. This describes how X is distributed. And now it's easy to prove things about this probability. So the expectation of X, let's in fact prove the expectation just as an example, right? So we have to sum over the values that X get. It's either 0 or 1, right? So it gets 0 with probability X equals 0, and probability of 1 with probability of X equals 1. And this is, of course, just 0 times whatever plus 1 times P. So this is just P. So the expectation is P, the variant of X. At this point, I'm going to start just copying the formulas. If you're interested why they're true, look on the class notes. Okay. Okay. Another distribution that's going to play a big place in this course is binomial distribution. Binomial distribution is just you repeat. So this is written as BK and P. So what is this? This is, N here is you're doing N Bernoulli trials and you add up the results, right? So you're flipping a coin N times, each time with probability P for a head, okay? So this is N, the number of flips. This is the probability in the B trial, okay? And K, this is, here we want to write down what is the probability. So probability of getting K heads. Okay. So formally what we're going to do, here's what we're going to do. Y is going to be a sum of x1 plus x2 and so on plus xn, where x1 to xn are Bernoulli of P, and they're independent. Okay, so the random variable y is the variable that has a binomial distribution, and this thing is of course equal to n choose k, right? P to the k times 1 minus p to the n minus k. To remind you why it's true, n choose k is the number of ways you can generate results of n experiments, right? The coin flips, such that k of them are heads and the rest are tails. And for a specific one that you select, the probability of getting k heads is p to the k, and the probability of getting the n minus k tails is y minus p to the n minus k. Okay. So this is the binomial distribution. The expectation of y is np. That's immediate from just using linearity of expectation. And the variance of y, right? This is the variance of the sum of the xi. And it turns out that this is very important. This is variance is also linear, but only for independent variables. Otherwise, it's not true, right? So, so remember that in general, you cannot, there is no linearity of variance, but if they're independent, there is, and that's what one can use here. So that implies that this is NPQ. Q is just a complicated way of writing 1 minus p. People do it just to get something a bit clearer. Okay, there is also geometric distribution, which is essentially you flip a coin with probability p, and the question is how many times you have to do it until you get a head. And so right, so this is how many times you have to flip a coin till you get a head with probability p for a head. So the expectation of x, this is very interesting variable because x can get values, right? X can get the value 1, 2, 3, right? Any positive integer, right? So it's but nevertheless, the expectation of x is 1 over p, which I think I mentioned last lecture, and the variance of x is so computing the variance of geometric variable in fact requires some blood, or you just open Wikipedia, of course, but the class does have the proof. It's not too difficult, you just need to do some math. Okay, I'm just mentioning it as something that would be useful. Okay, this was all the probability background, and hopefully, that would be for a while the boring stuff. Are there any questions before I move on to more interesting stuff? Okay, so let's do the interesting stuff. I hope you're still there. So we already spoke about 2SAT and 3SAT in the previous lecture. So let's speak a little bit about kSAT. So what is kSAT? kSAT in general is a formula. It's a formula that is in CNF form. So remind you, CNF form is an end of clauses, right? And every clause, it's a Boolean formula, of course. Every clause is the O, what we, that's what I mean, or V כזה, V, of exactly K literal. And the interesting stuff here is that the important requirement here is that all the literals are different. All literals. Okay, so no cheating by repeating the same variable many times. So I mentioned in the last lecture that for 2SAT, deciding if there is satisfying assignment can be done in linear time, and I presented the an amazingly simple randomized algorithm that also worked, although I didn't analyze it. And then, of course, I mentioned 3SAT, which is one of the standard NP-complete problems. So we cannot compute it in. We cannot find a satisfying assignment at polynomial time unless P equal NP, pigs can fly, and etc. etc. Now, it's a natural thing to ask, okay, I cannot find a satisfying assignment. Maybe I can find a decent assignment, right? So let F be the given kSAT formula, and assume it uses n variables as it has m clauses. And we are interested in the following problem, max kSAT.
Compute an assignment that satisfies the largest number of clauses.
So this is kind of interesting, right? Because think about, I give you a formula, and if it's a 2SAT, you can check whether it's satisfiable or not. But let's say the formula is not satisfiable, right? So you run the algorithm, it tells you, no, it's not satisfiable. But then you say, okay, fine, don't give me a satisfying assignment, just give me the assignment that satisfies the largest number of clauses, right? It's an optimization version of 2SAT. And the shocker, I find it very surprising. So let me set it as a theorem. 2SAT is NP hard. So what do I mean by that? I give you a two-set formula, and I ask you to give me the assignment that satisfies the largest number of clauses. This problem is NP-hard. We cannot solve it in polynomial time unless interesting things happening to the pigs. They fly and stuff. So, and P equal NP, etc., etc. So this is really surprising, right? Why is it surprising? Because if I give you a formula, a two-set formula, and I ask you, is it satisfiable or not? This we can do in linear time, right? So it's kind of, it really says that deciding whether a formula is satisfiable and finding the largest number of clauses that can be satisfied are fundamentally two different problems, right? And in fact, I guess by now it's 25 years ago. 25 years ago, this is essentially it's called the PCP theorem. Okay. Prove the following: given a three-set formula, the claim is slightly more general. You say that for every epsilon constant, you cannot satisfy more than 7/8 plus epsilon m, right? So you cannot do significantly better than 7/8 of the clauses, satisfying the formula. So let me maybe repeat this because this is extremely bizarre. I give you a formula, a three-set formula, okay? And this three-set formula, it might be satisfiable, right? But I'm not asking you for the satisfying assignment. I'm just asking you for an assignment that satisfies strictly more than 7/8 of the clauses. Finding such an assignment, a partial assignment, right, that satisfies more than 7/8 of the clause, this problem is NP-hard, which is, I think, is extremely surprising. And the reason why it's so surprising would become hopefully clear shortly. So this was a huge result, by the way, this PCP result. It led to a huge field in complexity theory and so on. So now, of course, the question is why it's so interesting. So let's try to come up with an algorithm that does something, right? So I give you a formula F. Let's do three-SAT, just F is three-SAT. And again, M clauses. Right, so let's look at a specific clause, X or Y or Z. In fact, I'm not even going to, just for this example, I'm going to just, the clause is a O of three variable, okay? And now what I'm going to do, I'm going to pick a random assignment. Right, so I'm going to pick, every one of the variables. I'm going to randomly pick its value between 0 or 1 with equal probability. Equal probability, half, and independently. Right? So I take the n variables of the formula for each one with probability half. I set it either to 0 or 1. And now it's a natural question to ask, let's call this clause C, just to get things concrete. What's the probability that C is satisfied? Anybody can tell me what the answer for that is? This is the probability that X or Y or Z is equal to 1. What is this? What's this value?
1/8.
No, it's the complement, right? So for x,
Oh, sorry.
no, it's completely fine. You know, you were in the right direction. So let's think about x or y or z. This evaluates to, so in fact, you know what, let's in fact do it, what you said. Let's think about the probability that it close evaluates to 0. For that, this happened only if x is equal to 0, y is equal to 0, and z is equal to 0, right? The probability of that, because x, y, and z are independent, is the probability of x equals 0, probability of y equals 0, probability of z equals 0. Each one of them have probability half, right? Because we set the variable probability half to be each of the values. So this is just going to be half times half times half. I want half, so it's 1/8, right? This probability is the complement, right? It's 1 minus 8. So it's going to be 7/8. It's a bit. Okay, so great. I have an algorithm that for one clause satisfies 7/8 of the clause on average. That's great. But what do we do about the general case? Are there any questions?
Just a quick note. When doing the probability of x and y and z, you have or instead of and.
No. Here, this is the
bottom?
clause. Here's the clause, right?
Okay.
Here I'm asking what's the probability that this clause evaluates to 0, right? So the clause is x
Okay.
or y or z, right? But for this to evaluate to 0, I need to have your, okay, so maybe I should write this. This is a bit bizarre, so let me write it in fact. Good point. It's a bit confusing, I didn't realize that. This is the probability of x equals 0 and probability of, sorry, x equals 0, y equals 0, and z equals 0.
Okay.
Right?
Got it.
Yeah, no, good point. Thank you. Because I skipped this step. And then I use the fact that you can write it as the product, right? Because they're independent. Okay, so now the question is, what about the general case where we have more than one clause? So first, if you think about it, the analysis about the clause it didn't really matter whether the variable were a variable or a negation, right? Because things are symmetric, right? So if a variable is negated, a variable is negated in the clause, it's the same thing. It doesn't matter. So we get the following. So if f, so let's assume that f is just C1 and C2 and Cn, right? So what did I just argue? I argued the probability, if I look on a specific clause Ci, the probability that it's 1, i.e. it's satisfied, right? This probability I just argued is 7/8, right? And in fact, if you think about it, it's exactly 7/8 because there are 8 assignments, 7 of them satisfy the clause. There is only one assignment, which is bad. Okay, and now what I would like to claim somehow that this means that 7/8 of the clause are satisfied in some sense, right? So let's do it formally, right? So I'm going to define xi is going to be 1 if and only if ci evaluates, ci is satisfied. Okay, and it's of course 0 otherwise. Okay, so as I mentioned, xi is an indicator variable. Okay, now, so you can think about this algorithm as randomly assigning the the values to the variable, and then for every clause, I just go and evaluate the clause. For every clause, I get an indicator variable, 1 or 0. It evaluates to 1 or it evaluates to 0. Okay, the number of satisfied clauses, let's call it y, number of satisfied clauses this number is just going to be the sum of the xi's, right? Why? Every clause contributes 1 to the summation if it's satisfied and 0 otherwise. Right? So this is exactly that. So what is the expectation of y? How many clauses are we satisfying on average? This is how many clauses are satisfied on average. Okay, so this is the expectation. It's the expectation of the sum. We just put in the definition, I going from 1 to m. Right? This is the sum, I going from 1 to m. I'm using the linearity of the expectations, right? This is, I promised you that this is a powerful property. And here it is, by linearity of expectation. You should tell your parents that their expectation should be linear. I'm sure they would appreciate it. By linearity of expectations. Okay, and now, okay, let's think about what is the expectation of xi. In fact, I did this calculation before. Let me do it again. Right. So xi is an indicator variable, so it's either get the value 0, the probability of xi to be 0, or it get the value 1, the probability of xi to be equal 1. Right? This is really the probability of xi to be equal 1. So, by the way, this is the reason why indicator variables are so amazingly useful, because the expectation is just the probability of the event that we care about, and we just argue that this is 7/8, right? So going back here, we get some I going from 1 to m of n 7/8. So this is 7/8 of m. Ta-da! Okay, so what we did, we argue that now on average, in expectation, this idiotically simple randomized algorithm satisfies 7/8 of the clauses. This is kind of shocking, right? And it's shocking because of the PCP theorem I mentioned earlier. You cannot do better than 7/8. So the best you can do is by an idiotic algorithm, which is always, you know, unless P equal NP and so on, which is kind of amazing. And you cannot hope for a simpler algorithm. And there is another amazing property of this algorithm. This is one of those things where only randomized algorithm can do. This algorithm didn't even look on the formula, right? It just randomly chosen the value of the variable and says, here you go. And in expectation, you're doing well. Okay, I want to ask you a question that would motivate the stuff I'm going to do next. Yeah, that's nice, but this is not good enough, right? In some sense, because you run the randomized algorithm and maybe, yeah, on average, you satisfy a good number of clauses, but maybe the random assignment you get is terrible. It satisfies only, you know, a tiny fraction of the clauses, right? What do you do then, right? You know that there is a good assignment, you just need to try, but somehow, so, you know, it's a randomized algorithm, so you just run it again and again, you know, you run it, whatever, 100 times, right? And for every one of the time you run it, you compute how many clauses it satisfies. And of course, you return the assignment that satisfies the largest number of clauses. Right? And I would like to claim that this algorithm might not, in fact, satisfies, the best assignment I found might not satisfy quite 7/8 of the clauses, but it has to satisfy almost 7/8 of the clauses with very good probability, right? If I do it itself 100 times, 1,000 times, it should be, the probability should be better that I'm getting very close to 7/8 of the clauses. By the way, I should mention one of the benefits of this PCP theorem is that they come up with formulas where all the clauses, you have formula where you cannot satisfy more than 7/8 of the clauses, right? That's inherently what's going on. So 7/8 might be the best you can do for a specific formula if it's not satisfiable. Okay, so we want to get something. So let me repeat again what I'm trying to say. I have a randomized algorithm working expectation. I would like to get, I'm willing to run it several times to get a better result, because I can just, every time I run it, I can take the result, what it returns and measure how good it is and return the best result. And if I run it t times, the question is, how good is the result I'm getting if I return the best result out of the executions? Okay, and this already turns out to be not easy to answer. We need another tool to be able to do that, and that's what I'm going to speak about next, if I have the time. I do have the time. I might not have the time to, well, let's see. I might not have the time to show the application, but I definitely have the time to speak about it. So Markov inequality. Okay, so what is Markov inequality? So we have a variable x, and it's a real random variable with real values. Okay, and the claim is that the probability of x to be larger or equal than t is smaller than the expectation of x divided by t. So this is Markov inequality. The proof is very easy. Let me try to do it, in fact, without doing the math. Okay. So think about the variable as just getting positive values.
Professor, sorry to interrupt, but shouldn't it be an inequality as opposed to an equality?
I wrote equality.
Yeah.
No, I wrote inequality.
As in, like, the probability, shouldn't it be bounded by the expected value?
Oh,
that's sort of
yeah. Sorry.
Yeah, no worries. Thank you.
In the worst case, yeah. One can prove, in fact, that it can be equal. But yeah, it's inequality. Sorry. I don't know. I was thinking about the fact that, in real life, usually we want to get equality, right? Fairness and equality. But in mathematics, you always want inequality, because somehow inequalities are much more useful. So, okay. So think about the random variable. It gets value between 0 and infinity. You can think about it as being some kind of, well, you definitely don't want to think about it like that. This is the distribution. So distribution means that for every value, the value of the function is the probability, the function is the probability of getting this value, right? So there's probability of x equal x. I'm here using a continuous function just for the discussion, but if it's a discrete function, just think about it as a histogram, right? For every discrete value, I would have a bar, and it would be the total sum. The area under this curve is 1, right? This is what it means that the probability is 1, right? Okay, now we have the average value, right? This is the expected value. Okay. And now, what does Markov inequality say? First, Markov inequality is interested only for t larger than the expectation, because if it's smaller than the expectation, this side is going to be larger than 1. Probability is always smaller or equal than 1, so who cares? So we care only about t larger than the expectation. Okay. So we have t, and we are speaking about the probability of x being larger than t, which is this area. Right. Now, the way you can kind of think about the expectation as being the center of mass at some level. So the idea is that if this blue tail is too heavy, right? If this is larger, think about the case that this expectation probability, oops, that was bad. If this probability is strictly larger than what the statement claims, right? If it's larger than this, then all you do is just essentially do the calculation and shows that the expectation must be to the right of the expectation. It must be somewhere here, and that's a contradiction. Okay, so that's the proof. If you want the math proof, it's in the notes. It's again very easy. It's one line of calculation, but somehow I hopefully this is more convincing. And anyway, hopefully you had seen this stuff before. Okay, so why do we care about this? That's a very good question. So I think I have enough time to show exactly this application I wanted to mention. Okay, so let's go back to the kSAT problem. I give you a formula F with M clauses. And again, we're running the same random algorithm that randomly assign values to the variables. But now I'm going to define the complement variable, complement in double quotes. This is going to be M minus Y, which is going to be the number of clauses. The expectation of Z is just going to be M minus 7/8 of M. So this is going to be 1/8 of M, right? Okay, now let's think about the case where let epsilon be some parameter. Just pick some constant between 0 and 1. Let's say epsilon is equal to 0.1. Okay. Now we can ask the question is what's the probability of Z to be larger than 1 plus epsilon of 1 over epsilon of 8M. Right. So what is this? This is the probability that you run the algorithm, and instead of satisfying the number of unsatisfied clauses is slightly, it's bigger than it should be. Instead of being 1/8, it's 1/8 times 1 plus epsilon. Right? It's slightly bigger, right? It's by 1% bigger, sorry, 10% bigger than it should have been, right? So now we can use Markov inequality, right? Because Markov inequality says this is equal to probability that Z is larger than 1 plus epsilon. Let me try again. Larger than 1 plus, okay, 1 plus epsilon of its expectation. And this is just equal to the expectation of Z, smaller equal, of course, as usual. And the expectation of Z divided by 1 plus epsilon, the expectation of Z. This is Markov inequality. And this is, of course, 1 over 1 plus epsilon. Okay. And if you think about it, this is smaller than example with, this is smaller than 1 minus epsilon over 2, for example. Okay, you can calculate it. Okay, why is this interesting? It says that I'm running the algorithm. The probability that the unsatisfied clauses is by a factor of epsilon larger than what I want is smaller than this. There is a small probability, right? Now, for the algorithm, if I run it t times, all the execution have to fail. Right? The probability that all the t execution fail is smaller than 1 over epsilon 2 to the t, and this can be made to be extremely small by taking t to be something like of 1 over epsilon. Why this is true, let's not go into it now. But you can make this probability very, very small by just running it roughly 1 over epsilon time with probability of, constant probability, you will get that one of the execution must have not satisfies a number of clauses very close to 1/8. So you're getting one of the execution will give you a very good assignment. Okay, that's all the time we have for this lecture. Sorry, I stole 1 minute of your life. I apologize. I usually try not to run over time.